Hi everyone, welcome back for day 2 of our mini Jamboree hosted by iGEM Concordia. Before we get started with our first speaker, I would like to welcome everyone to update your names with your pronouns if you want to. And so yeah, let's get started. So our first speaker for the day is Scot Bryson, the CEO and founder of Orbital Farm Circular Project. So Scott started original Orbital Farm in 2018 and is now in the process of building closed-loop systems that can produce vaccines and medicines for billions, hydro energy, and food production for all around the world from water, CO2, and electricity. Orbital Farms will build 200 circular mega projects around the planet to support and feed billions of people here on Earth today. And spend next 20 years prototyping, developing the technology to feed people in space in the future. So yeah, I would like to welcome Scot Bryson to start speaking and present this project. Well, his company. Thank you very much. Thanks for coming.
Great, thanks very much. Thanks very much for having me. All right, well, thanks everyone for spending the time this morning. I'm Scot Bryson. I'm the founder of Orbital Farm. Orbital Farm is a project development firm that's pulling together the technologies required so that we can produce food anywhere we want, whether that's in an arid region on the planet or whether that's off planet and somewhere else, so that we have the capability of living on the moon or on Mars in the future. Our planet is a fragile ecosystem. We have an incredibly thin atmosphere that we've been changing, and this has a dramatic effect on everyone here on this planet, whether it's extreme weather events, whether it's crop and food production. Everything is changing. But one thing that does bring us everything together is food. You know, whether it doesn't matter which culture you're from, doesn't matter what part of the planet you're from, food is one of these unifying elements that you know, when you meet somebody new, when you're sharing stories with family, this is where we what is deeply ingrained in us as a human species. And the ability for us to produce this food is not currently equally distributed around the world, even though we all have an equal need for consuming food. But the one of the other major challenges is that around the world, the number of hungry people that have been existing every year this number has started to go up in the past 5 years, and this is the first time that we've previously made massive progress in our agriculture systems and the way we've distributed food. And in 2017, we had 821 million people that were hungry. This number is set to almost double as we've moved through the pandemic and affected supply chains, in fact, affected locking down systems globally. And this has a major ethical challenges for us to all get over. But these are solvable problems because the technologies that we've invented over the course of hundreds of years, these have the capability of producing food in many of these different places. And as the world does continue to change, and as the climate warms, what this causes is a major problem in the predictability of how climates operate, how agriculture systems are productive, the yield that crops are able to produce. If the spring rains last too long or come too strong, and this floods fields, and farmers can't plant seeds to actually begin growing and germinating before the season ends. This is a major issue that we see, and frosts coming earlier, or hailstorms coming so strong that they destroy earlier crops or even mature crops. And these challenges put significant more volatility and pressure on our ecosystem. This on top of the fact that, you know, we're growing, and we're growing at a point where we're going to have 9 to 10 billion people in the next 30 years. This is a dramatic change from where we're at. And what this means in a linear model of how our system grows, we need to increase our food production by 70% to cover those additional people. And the reason behind this is because of our animal agriculture systems, our protein side of our food chain really is incredibly inefficient in terms of how much food it takes to feed those animals, and then the amount of food that we get from those animals that we can actually eat at the end of the day. This supply chain system has incredible numbers of inefficiencies built into it. That on top of the fact that we're wasting 30% of all food that is created and 50% of all fresh food. These issues are systemic and really point to this. We need to increase a significant amount of food production. And the problem is that agriculture right now takes up incredible amounts of land, where we've deforested the size of Africa and South America combined, where we've already overfished many fisheries in our oceans to the point of full collapse. So where is this 70% increase going to come from to sustain this massive growing population? Well, closed systems, or greenhouses in this example, these have been around for a very long time, and there are millions of these around the world. This is here in Spain, where you see hundreds of thousands of greenhouses clustered together in these groups. And we've had this capability of growing food and extending seasons and maintaining the control of these ecosystems to be able to produce food in a reliable and consistent fashion. But the problem is that these are not equally distributed, and the systems in order to enable these growing of crops in these different areas are not able to be financed or built or structured in many different places around the world. And what we've done is, through our agriculture system and through our manufacturing process system and through the process of all these technologies and the way that our businesses are financed, we've built a system of a linear economy where we take resources, we make and produce a product, we'll use that. When we're done with it, we'll dispose of it and cause pollution, or we'll bury this, or we'll dump it into our oceans. And the system has continued for as long as, for the most part, as long as we've been around. And what we need to move to is to a more circular systems, where we look at these waste streams as assets and resources, and we recycle the products that we're making and the waste streams that we're producing, and utilize these in the most efficient way possible. And this is critical when we're thinking about how you develop these technologies in space, when we're going to the moon and when we're going to Mars, to build any sort of sustainable system. And we need to apply the same thinking here on Earth. And we don't have to go too far. NASA and different space agencies around the world, they've spent a significant amount of time developing the capabilities for closed loop systems that allow us to recycle almost all the water on board the International Space Station, where it allows you this capability of looking at all of the different processes or the assets that are produced within a system, and solving those problems to be able to utilize this. So the carbon dioxide that you see here in this schematic is being vented. So if you're going to go for a mission that's longer than a year, that's not really a possibility. We need carbon, and we need carbon to survive for the foods that we're producing. And so if we continue just to vent the CO2 that each human breathes about 1 kilogram of CO2 every day, and if we vent that out, there's no longer going to be enough carbon to sustain that system, and it will eventually collapse. So what NASA developed in the late 60s was this. They took a look at ecosystems, and they said, well, little microorganisms break down waste products in part of what's called the dark ecosystem, and they break down these nutrients, and then small little crustaceans will eat those, and then bigger fish will eat those, and we can replicate the Earth ecosystems, but in a controlled sort of fashion, and even spinouts and commercial entities. And this is a product you can buy right now, and this is a mini ecosystem with small little single cell organisms that are consuming the CO2 and inorganic ingredients. They then themselves, as they grow on the surface area of this coral, they create food for the little shrimp. And these little tiny shrimp, they eat these little single cell organisms, they themselves grow, and some of these systems last for 7 to 14 years even, where these are completely closed and contained systems. And we've gotten to this capability of producing these tiny small scale versions because of the deep understanding of these closed systems that we've got. We've also done this as a society in large scale. This is Biosphere II, where we have a massive closed containment system of greenhouses. And this was meant to build and prototype technologies and this integrated system of how you keep everything closed with humans in the loop. And this program that was developed in the 80s and into the 90s, it's now part of Arizona State University. We've learned many different things, from social challenges of actually having people within contained systems, to the fact that there was excess amounts of CO2 in the atmosphere of these greenhouses, and there was a lack of protein that they had to consume. These were major challenges that saw to the project coming to an end earlier than they had hoped. We've also developed a lot of capabilities within the commercial industry, where we have vertical farming technologies taking off. This is AeroFarms, where again they're utilizing a NASA-based technology which basically sees the misting or fog within delivering the nutrients and the water requirements for the plants as they grow. And these systems are incredibly water efficient, but again, they're still within the linear economy world, where they're completely isolated and producing microgreens for downtown Manhattan and New Jersey, which is fantastic, and the ability for us to bring food production to the East Coast, where over 90% of lettuce and leafy greens are produced in California and the West Coast. This is an example of how these technologies can really be brought to different areas, and that the capability of bringing that food production to different places. And food really does have this capability of bringing people together, of providing nutrition and health to people. And you can produce many different types of foods beyond leafy greens within closed systems. You can produce single-cell organisms, as we've been learning the past couple of days, and the iGEM teams are working on. You can produce plant crops. You can produce fish within closed systems and recirculating aquaculture. And one of the big things that, before we began Orbital Farm, one of the things that we realized was the gap wasn't actually in the new technologies that needed to be created. There are fantastic companies that are developing this. The gap is actually pulling these pieces together and understanding the system integration of these systems and the proliferation of these technologies in many different places around the world. That's the really big need. And this is what we're keenly focused on doing, is building and developing our company to help support that, to help support the technologies, to help support the researchers and universities and the scientists working on continuing to close these loops and utilizing waste streams and turning them into value products. And we're going to do this by building many different projects around the world in some of these high need areas. And we're going to develop the capability to finance these projects and attract investors to deploying capital in this way, so that we have the capability of producing food, so that we can develop food security within countries, and beyond just food, have the capability of producing other products as well, like vaccines. So the market that we're working in is growing incredibly quickly globally. 10 to 20% range of growth year over year. This is an incredible amount of new production and capability, but also great opportunities for investors. And this is an important piece to figure out, because these technologies have been around for a very long time. And it's the alignment of interests of capital, and the alignment of interests of researchers, and the alignment of interests of the local population and what their needs are. This is really where this gap is. And this combination of these technologies will really allow us to produce food in desert regions in sub-Saharan Africa, or in northern climate regions way up in the northern part of Canada or in Europe. And these systems, the way that we have envisioned our systems, has really been around these systems that include greenhouses, that include aquaculture, that include bioreactors, and that include energy production, so that these truly can be these systems that are operating in remote areas. And so we combine together vertical farming and the biotechnology systems all together to be able to integrate these systems into a closed loop fashion. And so one of the organisms that we look to license for development of single cell proteins is really this beginning phase of looking at existing waste streams that we can utilize that are universally available in different places around the world. And so, we have CO2, we have water, we have nutrients and wastewater streams, and we have energy. The wind is blowing, the sun is shining. In fact, these are the areas in the northern climates where the wind is blowing strong, where there is major food insecurity, and where the sun is shining so bright that desertification has begun to take place or is already taken place. And these areas end up being the low-cost energy places. And with a system like this that can utilize these waste stream sources, you now can start to pair yourself alongside other industrial processes. You can locate yourself in technology parks that otherwise would never have agriculture systems. But the important part here is to think about closed loop systems, and this is only one pathway. But a bioreactor system and biotechnologies allow us to take different types of waste stream sources, whether that's leftover sugars, leftover in wastewater streams from sugar processing facilities, or utilizing methane as another input where you can use methanotroph organisms to convert that energy in that gas into a single cell protein product as well. And the example that you see here on screen are what are called hydrogenotrophs. And these derive their energy from hydrogen, and they take their carbon from carbon dioxide. They're part of the null gas microbe class. And you take these ingredients and you put them together into a bioreactor, and these single cell organisms grow, and they produce, and themselves they'll grow, and they produce an amino acid profile just as the same as fish meal. There's also another strain that's been optimized to produce an amino acid profile that's the same as whey protein powder. And these amino acids are perfect building blocks for the development of both an ecosystem within our systems, but then also as a component, as an ingredient to be sold to other CPG companies, to be able to sell or produce high moisture extrusion products or meat analog products. And you've got a very flexible platform that can be used in society in economies. And so what we do is we'll grow that protein, we'll use a portion of that to feed fish within an aquaculture system, and then we'll utilize the wastewater stream from aquaculture system to be able to utilize the nutrients that are left over and the ammonia that is produced as the waste product of fish. And that ammonia then uses microbes, two different sets of microbes, to convert from nitrates to nitrites. And that now provides the nitrogen requirement that plants need to be able to grow. And so you can cycle that water from your aquaculture system into your hydroponic system to be able to grow those plants. And that as long as you're sizing the right number of fish and the right number of plants and the flowing that water at the right pace, you're now able to build a system that is nearly closed loop. And with these systems combined, microbes are at the core of making this system function, just like everywhere here on Earth and just like everywhere in our bodies. And so we use different technologies from around the world. This is the most efficient greenhouse system in the world, where this system will produce 500 plants every single day on a single disc here, where you are utilizing almost 100% of the space because you're planting your seedlings at the very core in the center of this disc. And then as it slowly moves out to the outside edge, you harvest your full-grown plants that have, again, you've got no wasted space. This means less water, this means less heating energy requirements, this means less lighting requirements. You've got this physically optimized system. And what you can do with this system is you can now start to imagine this into moving into vertical farming systems. And so we have a design here to be able to create different greenhouse systems, but all connected within a larger system. And this allows us to grow different types of products in different greenhouses to produce different things. We can utilize these to produce plants for food, but we can also utilize these to produce proteins, and these proteins can be used to even produce vaccines themselves. Since the early 90s, we've had this capability of developing the possibility of producing vaccines inside a plant. This allows for a new delivery mechanism because the plants can be edible. This allows for the plants to become the bioreactors themselves. And so, it's an incredibly rapid and fast an accurate system to be able to target the types of proteins that you're looking for, and to be able to produce many different types of vaccines with the facility. The general process is you're synthesizing a virus that is a target vector or a target that you're looking to develop a solution for. You create a bacteria that then infiltrates the plant itself, and once this is done, the plant actually incubates that and grows for 7 to 14 days, somewhere in that range. And then you harvest it, and you can turn this into a plant smoothie and create an injectable or edible type of vaccine. And so this versatility between food and medicine and health really is this very interesting intersection, because what both of these elements require are these closed containment systems and closed ecosystems. And we need hundreds more of these facilities built around the world. And again, this is where we're focused. Where this can take us into, advanced robotics and automation systems to be able to improve that process further. This can take us to even smaller systems. This is an example of a company called Modular Farms that is no longer around, but is a great example of an indoor shipping container system that can be utilized to grow different types of products in really any environment. And we can grow many different types of vaccines and plants and foods, but also different single cell proteins in our bioreactors. I don't need to explain what a bioreactor looks like and how this is. We're very familiar with bioreactors in the brewing industry. This is just a little bit further information on the gas fermentation, the hydrogenotrophs that are consuming these types of products. The aquaculture systems that we utilize are also incredibly efficient, and they utilize space but produce hundreds of thousands of fish per year, to the order of 1,200 tons of fish per single facility. Again, built-in circular systems, the smaller fish optimized to grow in the center, and then as they grow, they move to the outer rings. And there are many of these systems that are already in place around the world, just separated in different places. And they produce some of the top salmon products in the world. And salmon is one of the most efficient food conversion systems that are out there. They convert about 1.07 kilograms of food that goes into a fish, creates about 1 kilogram of fish itself. Power is another critical component if you're looking to develop projects in remote areas. And development of solar projects and wind projects, and how these systems integrate together is a critical part of our work. And storing some of this excess energy in form of hydrogen can not only be an energy storage mechanism for our projects, but also is a key input into our bioreactors as the energy source for our microbes. We're developing projects at spaceports, and so right now we're looking at developing a project at Spaceport America to demonstrate and showcase the technologies and utilize these assets to demonstrate to the people that are going to be the first space tourists on Virgin Galactic, and showcase and demonstrate this in the middle of a desert and produce food for them. And we've got a number of different projects around the world where we're in discussions with mining companies, with CO2 producers, with feed companies, and these different project opportunities, and showcasing the breadth of the capabilities and the possibilities of what a distributed food system and what a closed systems can look like in many different places around the world. And then we're developing and working on a system to actually finance these projects, and development of a financial infrastructure with bonds and climate-focused bonds to be able to attract the capital required to make these projects happen. And some of the future-focused work that we're looking at doing is how you make these into large, beautiful systems, circular systems into tall vertical projects. This is future-focused work where we have a fully integrated system of multiple tiers and levels, and integrated between aquaculture, hydroponics, and bioreactor systems. And this is the Mars X house, the second version. This is an imagination of what a smaller habitat may look like, for a Mars base. And this is a fully 3D printed structure. This is not our work, but this is the work that we're doing, or precursor work that are required to utilize a platform in a system of this size and scale in future versions. And I want to close off here and just reiterate that, you know, space is something that is universal to every one of us. And since our earliest ancestors, we've all looked up at the stars with wonder. And this has been a source of our stories and our imagination. And we all look up at the same moon, and we all have dreams and wonder about this. And it has been, again, this underlying element between societies and through time. And this is now something that we think is, and we are sending people back in the next 4 years back to the moon from 50 years ago. And this can really become a unifying collaboration, just like the International Space Station was. We think that what we can develop is through food is a global collaboration for producing and reimagining our food systems and how they're integrated together and how they're deployed and built in many different places, so that we don't have to have over 800 million hungry people in the world when we have obesity problems and we have climate change that is going to exacerbate this problem much further. And so this is the work that we're focused on, and we're really excited to be partnering together with the iGEM teams, and really excited to be helping to support the initiatives that everyone here is working on. Yeah, we look forward to collaborating together with the universities, with technology companies, with consumer products and consumer companies. So thanks very much for everyone for your time, and happy to take a bunch of questions and answer whatever we need.
Well, thank you so much. Unfortunately, we're running a little behind, so we won't really have time for questions. But is there somewhere we can go to, like, is there a website or anything?
Yeah,
you can go find stuff.
You can check out some information at orbital.farm. That's our website. So it's there on the screen. Absolutely.
Awesome. I'll put that in the chat if anyone wants to check it out. That's awesome, though. I mean, as someone who's really interested in the biomanufacturing, I want to go into that later on. This is just kind of like an awesome way of doing it. So thank you so much for your time, and it was great. So thank you to SynBioApps, the NSERC-Create program, Concordia University, the Concordia Student Union, Promega, Dr. Katru, Orly Weinberg, and our mentors.